Hi everyone. Last time I talked about post-processing effects and how it's useful to have as many of them available as possible. So we have plenty of options when creating a game. And here we are again, because in this video, we'll be making something new in this category. This time, it will be a simulation of a scene viewed from beneath the water surface, featuring typical surface ripples and adjustable coloring. We'll only need a few lines of code, so let's get started. Since this is a post-processing effect, we'll need an image to which we'll apply our algorithm. As you may know from previous videos, I use a screenshot from our game for this purpose, so I'll start by creating the usual scene. Right-clicking on the folder Scene, create new scene. It should be a 2D scene, and let's call it Underwater. Okay, and as I said, we'll use a texture, so I'm dragging this image found in JPEG into the scene, which created a new node of the type Sprite 2D automatically, and in the inspector, we can cancel the centered in the offset category, and in transform position, let's reset it to 0, 0. And let's scroll down to the material section, create a new shader material, click it, and create a new shader, which is called underwater.gd shader, type shader, mode canvas item, and I'll just put it to the shaders folder. Create and click again to open it in the shader editor. Let's expand the window a little bit. And as always, we'll delete everything we don't need, leaving only the fragment function, deleting vertex and deleting white. Cool. So, as we saw at the beginning of the video, the effect is based on periodic rippling and a color filter, which together creates the illusion of an underwater environment. I'll start with the color, which I'll define as the first uniform parameter. So, uniform, vec3, it will be an RGB color, let's call it water, with source color as a hint, so it will create color picker in the inspector, and the default value would be 0.4, 0.6, 0.8. Okay, yeah, so this is something like light blue, as we can see here in the inspector and shader parameters. Next, we'll need the wave speed and parameters related to the frequency and amplitude of the resulting waves. I'll call these variables speed, wave, and warp. So uniform float speed with a hint range, and it should start at 1, and the range, let's make it from 0 to 4 with a step point 0, 1. Next, we have uniform float wave with another hint range, and this one should start at 20, and we'll make it from 0 to, for example, 100 with a step point 1. This is okay in this case. And finally, uniform float warp with another hint range, and this one will start at 5, and the range would be from 0.1 to, let's say, 20, and the step point 0.1. Okay, now I'll write the skeleton of the fragment function, and then I'll say a few words about the functions that will be best suited for our purpose. So deleting the comment, and let's start with the usual vec2 uv is UV. This time we don't need to move the origin to the center, and of course we don't need to fix any aspect ratio. Okay, and the time variable float time is time times speed, again the usual stuff. And finally the skeleton will be finished with the output. So the color is texture of our textured background image, and UV coordinates. So far, we don't see anything special because the shader is only displaying the image in its original form. But we can already apply the color filter, which is a simple operation of multiplying two vectors like this. So let's enhance this line, multiplying by vector 4 of our water, vector 3 and 1 for the alpha channel. Wait for it. Okay, if we show the whole image, we can see it actually has some kind of bluish tint. And if the image seems too dark, we can adjust the color filter's value or cancel it out entirely by setting the color to white. Let me demonstrate. So changing the color, and if I put it up to white, we are simply multiplying by a unit vector, which means no change. Okay, but for now, we'll leave this parameter as its default value. We want to create periodic ripples, which requires using periodic functions. As you can probably guess, once again, the trigonometric functions sine and cosine are the best candidates. However, we'll need to combine them a bit and also make use of a parameter that changes over time. Let me show you this in Desmos. So I'm switching to Chrome, and here I have the Desmos app open on the URL desmos.com/calculator. Usually I display just one function here, but this time we'll need two. The reason is that the water surface doesn't ripple in just one direction. It moves across the entire plane. So the resulting effect will be a combination of position changes in both the horizontal and vertical directions. So let's start with a simple sine function, sine x. What we have here is, of course, a periodic wave, but it's too regular and also static. So let's try adding the dynamic part of our algorithm. We'll multiply the formula by another sine function, and this time applied to the parameter t. So multiplied by sine t. So far nothing has happened because we still need to define this new parameter. So let's click this t, and we have a slider. I could move the slider manually to show how the graph changes, but that's not very convenient. And we have a better option. So I'll click this icon to open settings and change the animation mode to play indefinitely. And now when I click play, we can see how the graph starts to ripple nicely. So the wave is rippling, but we still need to move it in a specific direction. So let's modify the formula like this. We'll subtract t from x here. Perfect. The first part of the algorithm is done. Now we'll add the second part, which will be based on the cosine function and move in the opposite direction. So I will just click here to add another function and make it cosine of x, and this time plus t to make it move in the opposite direction, and multiplied by cosine of t. Okay, perfect. I think we've clearly demonstrated the formulas our code will be based on. And now it's time to write it down. So I'll switch back to the Godot engine. Switching back. And when drawing a graph, we needed to use the x value to display something. But now we'll be working with UV coordinates. So first I'll define a vector based on these coordinates, and that vector will change over time. Let's expand and write it here. So vec2, let's call it S, for instance, would be UV times wave plus time. Okay, and now we'll use the same functions we just saw in Desmos to create periodic changes in the UV vector. Because we're working in the 0 to 1 range, we don't want to shift the UV coordinates by too large a value, so we'll divide the result by 1000, that is, multiplied by 0.001 or 1e minus 3 for short, like this. UVX is increased by sine of Sx minus S dot y times warp, and as I said, multiplied by 1 e negative 3, which is 0.001, and multiplied by the second sign, Sy. Okay, it's already starting to ripple in one direction. So the Sy is representing the t parameter from the Desmos app. And now let's do the same thing, but for the y coordinate. So I'll copy and paste this line and do the changes. First, it should affect the y coordinate of the UV vector. Now we want to change minus to plus to give it the opposite direction. And finally, let's apply sine by cosine. Okay. And yeah, that's it. Let's show the whole image. Nothing else is actually needed. We've achieved the same effect we saw at the beginning of the video. And if we want, we can now tweak the parameters in the inspector to get slightly different distortions. So for instance, if I change the speed, it is waving faster or slower. And now let's modify the frequency, which is represented by the wave. And we can see, if I zoom in, that the waving is actually, yeah, it has a higher frequency. And if we, let's zoom back, change the warp, it should give it a higher distortion and a higher amplitude or lower. Yeah. Okay, let's revert to the default values. I mean, some parameter combinations might be useful, but personally, I like what we are seeing now the most, the default settings. Thank you very much for watching. As I said, you can never have too many effects for adjusting the look of a scene, and I'll definitely add at least one more before we reach our milestone, which is 100 shaders, all included in the Godot shader pack. I'm sure this kind of rippling effect we programmed today will find use in many games. For now, take care, good luck with your game projects, and I'll see you in the next video.